Welcome to our next section of notes. So yesterday we started talking about the math that we're doing on population growth, and today we're going to continue that by talking about models of growth. So the last video that I posted, we introduced a mathematical model of how populations grow, known as the exponential growth model. We noted that this model made a number of simplifying assumptions so that we could focus on the core idea that populations can grow exponentially over time and that this growth is faster in species that possess a high maximum per capita growth rate. The exponential growth model assumes that populations can grow without any limits, but we know that that is not realistic. The growth of populations can be limited by a number of factors. Some factors can reduce the size of the population regardless of the population's original size. Other factors have a stronger limiting effect as the population approaches the carrying capacity of the environment. So some density, there's some factors that can limit growth. When population growth is reduced regardless of the density of the population, we would say that the population is limited by density independent factors. So common independent factors would include droughts, extended periods of cold weather, floods, fires, tornadoes, and hurricanes. When these conditions appear, we typically see a drop in birth rates and an increase in death rates, which would cause the population to decline. These declines typically happen quickly, and such as a hurricane or a tornado. So with these factors, the magnitude of a population drop is not related to the size of that population. Both large and small populations are equally likely to experience a large decline. But when growth factors of a population is increasingly limited as its size increases, we would say it is subject to density dependent factors. So once again, when the growth of a population is increasingly limited as its size increases, we'd say that it is density dependent factors doing that. So a classic example of this is where we have two bacteria species here, and we are adding a constant amount of food daily. So this Russian biologist did this. And as expected from our exponential growth model, both species of paramecium initially experienced exponential growth because they were both getting food every day. Eventually, the population sizes began to plateau as the fixed amount of food added began to limit the population growth. So he did not increase the amount of food, he set the same amount of food. So at first there was abundant food available to these two different species of paramecium. But then eventually the food became a limiting factor as that population started to increase. So the paramecium started competing for that food. So that food shows that carrying capacity of the environment. So we would see that those populations in a low food supply and a high food supply exponential growth at first, but both would end up plateauing based on that limiting factor of food as the carrying capacity. So this logistic growth model is the mathematical model that incorporates that concept of those limited resources. So it's taking that carrying capacity of the habitat into play. So we begin with our exponential growth model that we discussed yesterday, and then we're going to incorporate the idea of carrying capacity. So in order to do that, we need to build on this model by adding some parameters that will slow down population growth as the population increases. So you could do this by including the parameter K representing carrying capacity, and then determining how large the population is relative to that carrying capacity. So we still got our change in population over time. We've got our max, our maximum per capita growth rate. So we have that here, but now we have the carrying capacity minus that population size over the carrying capacity. So adding this to the equation helps put in those limiting factors, that carrying capacity, into our growth model. Okay, so when the current population size is much smaller than the carrying capacity, the terms in parentheses of the equation have a value of approximately 1. So in this scenario, the few individuals present in the population are experiencing no limits on their population growth. So the model behaves much like our experimental, our exponential model. But however, when the population size approaches that carrying capacity, the term in parentheses has a value of approximately 0, which causes the entire right side of the equation to have a value of approximately 0. So when that change in population over time is 0, then the population is stable. So that's why we see it starting to level out here, because it means that it's neither increasing nor decreasing. So in this scenario, all individuals are severely limited by the available resources to the point that the birth rate would be equivalent to the death rate. So we will often see population overshoots and die-offs. So they kind of hover near carrying capacity, showing quick die-offs and quick overshoots, going over carrying capacity, then under, then over, then under. But we do sometimes see some crazy examples of this, like the deer of St. Matthew Island off the coast of Alaska. So this video here shows, it's kind of funny, but it shows, it's making fun of the deer. It's unfortunate, but it shows the reindeer of St. Matthew Island and really what happened. But they did experience exponential growth, as you could see here on the graph. Then they experienced a rapid die-off because their population was just so dense, and they ended up eating all of their food, and then we saw a die-off, and then they just couldn't make their numbers come back. So we see currently that when we're looking at human growth, we do see a bit of exponential growth happening here. But scientists are predicting that we will follow, we're hoping at least, that we follow the logistic growth model and we even out over time. We certainly don't want to see us experiencing a rapid die-off. That would not be great. But this slide really just explains that human population growth in the United States. Originally, we were thought to level out around like 91 million people. But obviously, we keep raising the carrying capacity of our planet. So we keep coming up with food, ways to create more food for our population. So that's the end of this particular note set. Hopefully you learned a little bit today, and I hope you have a good rest of your day. Thank you.